Okay, so we're recording now, so we can post this later if you want to view it. Go ahead on.
Like how can we place the test tube in a pan or any kind of thing to put in oven? I'm not sure
Well,
how we can do it.
if you put the materials in the test tube, and I happen to have a box like you have right here. Okay, so here's my hydrates lab,
Yeah.
and there are 4 test tubes in here. And before you put the material in your test tube, you want to make sure you know how much material you have. Also, this drywall here, do you see how those are solid chunks?
Yeah.
You may want to put it on your tabletop and crunch it up. And this is what I mean.
Oh,
So here, if you take a look at my screen after I share with you. Now I have a white background here.
I see. I can see.
So I got a chunk in there that won't come out. So what I'm going to do here is I've got a little tool that you use for nails to push your cuticles back. And I'm just going to go in there and try and break that apart so that carefully so I don't break the glass.
Okay.
So here I want to make this into a powder, so I can just take the jar itself and force it into the drywall with a little bit of twisting. And here, and this is just on a piece of paper, which is fine. So here you can see that I've kind of powderized it. Do you see that?
Yeah.
Now the amazing thing about this is that there's H2O in there, and I'm not going to call it water because clearly this is a solid and water's a liquid, right?
Yep.
Okay. So you want to be able to weigh this,
Mm-hmm.
but you also want to be able to weigh it after you heat it in the oven. So I'm not going to show you what to do next. I'm just going to put this in my test tube. Okay, so you can see it in the test tube, right?
Yeah.
Now, if I put this in the oven like this, is the solid coming out?
I don't think so.
No. Because it's a
Okay.
solid, it won't leak out, as it were, and you can just set the test tubes laying on their sides.
All right. All right. And
So
I have
now,
one more
let me ask you
question.
this, though.
Yeah. Sure.
How are you going to know how much material you have in there?
I think you should mask the test tube first, and then when you put material inside, you mask the second time, and you subtract
Okay,
it.
so why would you do that instead of massing this stuff before you put it in the test tube?
Well, seeing it powder like this, you may lose some of it, or it's
Okay, you
harder.
might lose some of it on the transfer to the test tube.
Yeah.
Okay, that's a good reason. What's another reason?
Uh, I think when you're masking the test tube with the material, and we subtract with the test tube, and you can basically you can calculate the mass of the material already in the test tube, and and then we can use that to do the experiment.
A little more detail. I think you're headed in the right direction, but I just want to hear you give me a little more detail about what you're going to do with that test tube after you heat it.
We masked it. We
So you're going to let it
masked,
cool. You're going to let
let
it
it
cool
cool and mask it.
down and mass it, right?
Yeah.
Do you expect the mass of the test tube and the material in the test tube to be the same or different if this is a hydrate?
I think after it's hydrated, the mass of the test tube with the material be less than the before.
Okay, and that amount that it's less, what is that number equal to? I
The
mean, what does it
high,
mean?
the H2O gets lost.
Right, it's the mass of the H2O lost. How are you going to make sure that all of the H2O has been lost?
I think we have to. That's kind of. um,
Because
Sin is a low color, so
clearly
I
you
think you
can't
have.
see it
Yeah, I think you have to hit it 2 times.
two
Maybe.
times. Why two times?
Because the last lap you burn the magnesium like 2 times. I think you can do it 2 times. Do it until it doesn't change the mass at all, and then I think the hydrogen is off.
That's what I want to hear on. I want to
Yeah.
hear not heat it two times. Heat it until the mass doesn't change anymore.
Okay. Yep.
Because if the mass doesn't change anymore, you can't be losing more H2O.
Yeah.
You're done. So
Mhm.
that's an important thing. Heat to a constant mass. That's a very common thing to do in chemistry.
Yeah.
Okay, good on. Does that kind of take care of that question?
Yeah. Take care of my second question too.
Okay, excellent. So the other thing I would suggest though on is that when you heat these things, don't get anxious and don't get in a hurry.
Okay.
Heat it for a half hour and go do some homework or go watch some TV or go for a walk.
Yeah.
Let it cool down completely before you touch it. So that means let it sit around for at least 15 minutes.
Yep.
And make sure it's completely cool to the touch when you weigh it. Now, if you're worried about your fingerprints on the test tube, what can you do about that? Two things.
Uh, I think we can count as percent error.
Nope,
No.
nope. How about if you want to weigh the test tube, you don't touch it with your fingers. Maybe
Oh, you clip or something.
you use the test tube clamp.
Oh, okay.
So you won't get any fingerprints on the test tube, right?
Yep.
But there's something else we can do. So here I have my balance or my scale, and I'm going to zero it.
Mhm.
And I'm going to try and place my test tube on there so it won't roll.
Yeah.
Oh, it is rolling. 19.06 grams, right?
Yeah.
Okay, so now you can see I'm touching it all over the place and putting fingerprints all over it, right?
Uh-huh.
If my fingerprints are going to be a problem, what will happen to the mass?
We would change the mass.
It will change.
Um,
And it's still 19.06.
mhm.
So this tells me that I can probably handle the test tubes with my hands because my fingerprints are so small in mass that they don't even measure on my balance. Does that make any sense?
Yeah.
So two ways you can handle it. You can use your test tube clamp,
Yep.
or you can test and see whether or not it matters.
All right. Got
And
you.
that's something that scientists do all the time. You know, we don't want to spend a lot of time being careful if we don't have to.
Mm-hmm.
So we might do something like that where you touch the test tube before, touch it after, and see if your fingerprints weigh something. There are labs that we do where you filter things and you end up with little black specks in there. And people always ask me, do those black specks matter? And I ask them, I don't know. How would you test for that? And the answer is take some black specks and put them on a balance and see if you can weigh them. If you can't weigh them, they don't matter. Does that make any sense?
Yeah.
Okay, good. How about you, Jessica? Do you have any questions?
You know, on the sorry, let me pull it up here. The lab from yesterday, the determining a formula from combining masses.
Yeah.
I got a little bit stuck at the end, and I feel like I was doing something wrong when I.
What was the last question, or what was the last part where you were getting stuck?
Well, it kind of wasn't, well, when I came up with the moles, I came up with these really tiny numbers and then I just put one on top of the other, and divided them. And then I couldn't quite find like in my notes the right information to go from there.
Well, let me ask you this. What did you get for the moles of magnesium?
0.00798 and then 19 were the two digits after the sig figs.
Okay, and we all should have gotten the same moles of magnesium because we all use the same magnesium strip per se, right?
Right.
What did you get for your moles of oxygen?
0.00775029.
Now you'll notice I'm using a unit and a label. And here's what I'm going to do. There's a couple of ways you can do this. I'm just going to put the bar over the 19 because it's repeating. Okay, so I know that this number belongs with oxygen, and I know this number belongs with magnesium. We can't have formulas that have numbers like this. So what we want to do is we want to change one of these into a 1, and the other one should be larger than 1. So how can I turn one of these into 1 and make the other one proportional? And the answer is divide by the smallest of the two. So these will be proportional. Now, I imagine that this, because of the balance, is only good to there because the mass was like 0.19 something grams, right?
Yes.
So that's 3 significant figures, and you should have used a molar mass that had at least 3 zig figs. So that means this is good for 3 zig figs. For the oxygen, it's the same thing. We should be able to get 3 significant figures. So that means here, when I round, I want to round to 3 zig figs.
Okay.
Now for the oxygen, since I'm dividing one number by the exact same number, it's exactly 1. Now what do we get for this other number?
Oh, okay. 1.02.
1.02.
I think that's what I came up with, but I did switch them.
That's fine. Now here's another way to do it. You do this. So you put one over the other. You put the larger one on top and the smaller one on the bottom. And you turn this, instead of into a fraction, you turn it into a decimal. And all decimals, whether we like it or not, are over 1. Are you with me there? So 10.2 is the same as 10.2 over 1.
Right.
6.5 is the same as 6.5 over 1. So all decimals are over 1.
Right.
So here, this says that you have 1.02 magnesium to 1 oxygen.
Right.
So either way, you get the same result. Here, you kind of see it in action.
So how did you go from on the second one that's not circled is what I had, and then when I divided them, I did get the 1.02, but I put it on for oxygen 1.02 rather than magnesium because I wasn't sure how you went from.
Well, look at my labels. Whenever you have this, so here's my label, inch and foot, right?
Yep.
So that means the 12 goes with inches and the 1 goes with foot. It's the same for here. 1.02 mole of magnesium is equal to 1 mole of oxygen in our formula. So if I have 1.02 moles of magnesium, I want to use that as the subscript for magnesium.
Okay.
So this is actually pretty good. It's the kind of number I expect. I must have done a good job. Now, and you did a good calculation. What is your percent error?
I got 2%.
Yeah, because your percent error is going to be what you got minus what you should have got over what you should have got times 100%, which ends up being 2%.
Got
Exactly.
it. No wonder. Okay, so since I switched the amount, I thought the oxygen was the one that was off. So then when I was doing the homework problems, I was really struggling to wrap my mind around. I was like, well, product,
Yeah.
I couldn't quite get it. I was like, man, this is really hard. But now
Yeah, if your oxygen number ends up being too high, it's a hard sell. It's hard to explain. Because if your oxygen number ends up being too high, it means you somehow or other measured your magnesium, and the number you had for magnesium, the mass that you actually had, was too low. That would give you that would make your magnesium number seem low compared to your oxygen number. So if you have oxygen 1.02, you have to think of reasons why the magnesium would be low compared to oxygen. So think of ways that that could happen. One is you lost your magnesium somehow or other before it reacted, or you added something into the crucible that wasn't oxygen and you weighed it. So what might we add into the crucible that would have mass afterwards? And the only thing I can think of is if you put it on the balance and maybe fingerprints.
Oh, okay.
Now, I'm going to be honest with you. In the lab that I did this in, you can't even measure fingerprints on that balance.
Okay.
So what are the reasons why the magnesium would be too large? And it's really two questions. Why would the magnesium be too large, or why would the oxygen be too low?
Well, I imagine that some of it kind of splattered out. And then when I had come up with my weights, I had subtracted, or I'd taken
Right.
subtracted the amount of magnesium we started
Exactly.
with.
So
But then it
when you
didn't
see,
make sense.
yeah, when you see the photo of the little specks, that means you lost product. And that means that the mass of product is going to be too low, which means the difference will be too low, which means your oxygen will be too low compared to magnesium. And here, this oxygen is too low compared to magnesium because it should be 1.02.
Right.
Okay. There are other reasons why you might have too little oxygen, but that is the most reasonable explanation. The most reasonable. The other explanation would be that your magnesium strip actually let me think about it, either weighed more or less than it should have. In other words, we measured it wrong. But you always want to go for the most reasonable explanation. You don't go for the far out, well, there happens to be an ancient alien civilization on this planet, and they like to mess with chemistry students. And that's why chemistry is so hard, because of ancient aliens. It just doesn't make sense. It's not the simplest explanation. You always want to go for some sort of cause and effect that you can justify. Okay, so do you understand now why the 102 goes with the magnesium?
Yes. Because
Okay,
the
good.
oxygen divided by the oxygen would be the one. Is that?
Yeah. So these numbers go with those particular elements. Excellent.
Thank you.
Any other questions?
Oh, I have on that paper too. That when can I write as a scientific notation or the mole of magnesium and oxygen?
Yes, absolutely. You can.
Yeah, because I write like as scientific notation and I calculate the magnesium mole, and turn out the formula will be magnesium 1.03. So it's not
1.03?
yeah,
Yeah, so
3%
you
error.
calculated that there's a 3% error.
Yeah. So I think because of the, I round up some kind of. So
Oh,
that's
yeah.
why,
And here I'm not rounding until the very end.
yeah.
And see, that's what can happen when you round as you go.
So is mine still good or it has to be fixed?
Oh no, it's just horrible, you're good. I mean, I think this means that you're going to be a liberal arts major. I'm kidding. You're doing a good job. You're learning as you go along. If you're learning as you go along, then you're doing what you're supposed to do.
Okay.
All right, on?
Yeah.
You sound like you don't want to be a liberal arts major.
I don't know. My major is still undecided yet, so
Oh, you haven't decided?
no.
Well, liberal arts majors usually go back to school and get science majors later.
Oh.
I cannot tell you the number of students that are in my class that have a liberal arts degree already. And they said, you know what? I just can't make a living, so I want to get a science degree so I can get a job. I'm not kidding. So I don't have anything against liberal arts. In fact, I think liberal arts is really hard. You know, I don't understand how people can write English papers. I don't get it. English is the most horrible language to write in because it's difficult. It doesn't make sense. They have 3 different words that sound the same thing and spelled differently. It's just silly. I don't get it.
Yeah, I know.
Science, at least, you know, it's all the same. The number 1 is the same number in all languages.
Mhm.
I love it. All right. Any other questions? Since you don't have any other questions, I'm going to take you on a journey where we left off last time, but we actually didn't do any of these problems. I kind of showed you how to do them. So first thing I'm going to say before I do this is that if you want to run away right now, I'm absolutely fine with this. You know you have an exam today and maybe you want to study for that exam on your own, but this is the kind of stuff that helps you think about things that might be on the exam. So we talked about how to do these last time, but we didn't do them. So we're going to take a look at some of these, okay? And again, if you want to bug out, I won't feel bad at all. All right, so here, this one we have the mass of 2.5 moles of compound with the formula ECl4, in which E is a non-metallic element, is 385 grams. What is the molar mass? So this is what I often use for the abbreviation for molar mass. And this is how you calculate the molar mass. Now, of course, we do not want to leave this in decimal form. So I'm going to do 385 divided by 2.5. And I think it's going to go in there 100 times, plus another, say, 25, plus another 6. So that's what, 126, roughly? $385 divided by 2.50, and we get 154 grams per mole. And of course, per how many moles? Per 1 mole. So this is the molar mass. So what is the identity of E? Well, we know the formula is ECl4, and we know that Cl4 is equal to 4 times 35.45 grams, which is 141.8 grams. So that means that when we try and find out what E is, we just want to take 154, subtract from that 141.8, and that'll give us the molar mass of E. So this looks roughly like it's 12.2 grams. So what has a molar mass of 12.2 grams or is closest to that? And the answer is carbon. So we're going to say that this is an element. The element is carbon. It is a non-metallic element. And you have carbon Cl4. And we can double check our work because we can get the molar mass of this stuff. The molar mass of this stuff is 12.01, 35.45, 4 times and see if we get this 154. And when we add these all up, what do we get? I get 153.81. And looking at those two values, do they seem to be about the same? And I'd say they are the same, because if I round this to the ones, I get 154. Are you with me there, folks? Good?
Yes.
Okay, so I'm going to go ahead and move to the next one. And remember, if you have a question, you need to stop me and say, hey, wait a minute. Calculate the density of the nucleus in grams per cubic centimeter, knowing that the nuclear radius is 4.8 times 10 to the minus 6 nanometers, and the mass of zinc 64 is 1.06 times 10 to the minus 22 grams. The volume of the sphere is 4/3 pi r cubed. And remember, we want grams per centimeter cubed. So I suggested before that rather than work with nanometers, that we change that into centimeters. So here's what this looks like. So you can see I put 1 nanometer in the bottom because I want these to cancel. What am I going to put in the top? I have to put something equal to this. So what's equal to 1? 1. What's equal to nano? 10 to the minus 9. What's equal to meter? Meter. So this has the exact same thing in the top and the bottom, except for the nano is in the bottom and 10 to the minus 9 is in the top, which is totally legal because nano is actually just an abbreviation, if you will, for 10 to the minus 9. And then likewise, I can do this. I'm like most people. I'd rather not deal with exponents if I don't have to. So when we do the work here, you can see that this is 10 squared minus 6 minus 9 and 2. You add them all up together and you get negative 13. Any questions on how I did that? And I didn't use my calculator because I just added these numbers up together. Negative 6 and negative 9 is negative 15. Negative 15 and positive 2 is negative 13. So now I'm going to get my volume, and it's going to be, now I really don't like the way this is written, but it's written that way for a reason. It's because you have a book and it's easier to write this all on one line. So you do the 4/3. And so a lot of people write it this way. And I don't like this either. To me, it's a little compromising. This is the way I like to write it. I want to know precisely what things are in the numerator and what things are in the denominator. This is the way I would write this. Okay, so we have 4 pi, and notice I'm using parentheses for the radius. So this way I know that the centimeters will also be cubed. And we can think about estimating this, but we don't really need to. We know that if you have 10 to the minus 13 times 10 to the minus 13 times 10 to the minus 13, it's going to be like 10 to the minus 39. So we're going to have 10 to some really very negative number here. So I'm going to do 4 times pi times 4.8 times 4.8 times 4.8 divided by 3. So I get 4.62 times 10 to the minus 2. And I know this is minus 39, so I'm going to put that together and get minus 37. And I get 4.63. So what am I doing here on?
It's a sig fig,
I'm not rounding,
not round yet.
not rounding yet. So actually I should put the arrow there because this is 2 zig figs. So I'm going to put my arrow to the 6 and I'm going to keep the 3. Fair enough?
Yeah.
Okay. And so now we have the density is 1.06 times 10 to the minus 22 grams over 4.63 times 10 to the minus 37 centimeters cubed. And this is our final answer. So how many significant figures are we going to have? Two. All right. And we can see that 10 to the minus 22 divided by 10 to the minus 37 is going to be 10 to the plus 15 on top, right? We can see this is going to be roughly 0.2 to 0.25. And so when we distribute this, we can actually make this 2 times 10 to the 14, where I take one of those 10s and multiply times that. So this is my ish, 2 to 2.5-ish times 10 to the 14. And let's see what we get. 1.06 second EE, negative 22, divided by 4.63 second EE, negative 37. And we'll get 2.28 times 10 to the 14. So we're going to say 2.3 times 10 to the 14 grams per centimeter cubed. And that's the density of the nucleus. If it seems like it's really dense, it's because it is. Remember, 10 to the 9 is billion, 10 to the 12 is trillion. So this is a 200 or 2,300 trillion grams per centimeter cubed. 2,300 times 10 to the, or I should say trillion grams per centimeter cubed. So that means if someone took that much in a centimeter cubed and dropped it in your hand, one of two things would happen. The thing would go right through your hand because it's so dense, or when it hits your hand would immediately be pushed to the floor because of the mass of the material. It wouldn't be like someone dropping an elephant in your hand. It'd be like someone dropping 1,000 elephants in your hand, all in one little centimeter cube. So does that sound dense?
Yes.
Sounds dense to me. Calculate the density of the space occupied by the electrons in the zinc atom. Given that the radius of the atom is 0.125 nanometers. Now, some people say, well, you know what? You need to calculate the volume where the electrons are and take the volume of the nucleus, which we calculated before, and we have to subtract the two to get the real volume of the electrons. Are you with me? Does that kind of make sense? Because the electrons cannot be in the nucleus. Well, let's calculate this volume here. So I'm going to take the 125 nanometers, multiply by 1 times 10 to the minus 9 meters over 1 nanometer, times 100 centimeters over 1 meter. So I'm doing the same thing that I did before. I'm converting to centimeters first. And here I'm going to get 1.25 times 10 to the minus 8 centimeters. Now I'm going to plug it into the formula for volume. And I'm going to do this one a little bit differently. I'm going to do this 1.2 parentheses 1.25 second EE negative 8 end parentheses, and I'm going to use this little caret button. Then I'm going to multiply by 4, then pi, and divide by 3. And I get 8.181 times 10 to the minus 24 centimeters cubed. Now, does this seem reasonable for this? Well, here's the way to think about it. What's 10 to the minus 8 cubed? 10 to the minus 24. What's 1.25 times 1.25 times 1.25? Well, I know that 12 times 12 is 144. So 1.2 times 1.2 is going to be 1.44. I know 13 times 13 is 169. So 1.3 times 1.3 is 1.69. So what's 1.25 times 1.25? It's about 1.5. What's 1.5 times another 1.25? Well, it's going to be about 1.9. So one of these plus half more. So what's pi divided by 3? 1. What's 4 times 1.9? Does 8.18 seem reasonable? Absolutely. Okay, so that's the volume. And remember how I said we want to take the volume of the electrons minus the volume of the nucleus? This is what that would be. This means change in volume, if you will. So here's the volume of the sphere, including the nucleus. And here's subtracting the volume of the nucleus. Guess what my calculator is going to spit out when I'm done with this problem? Oops. 4.63 times 10 to the minus 37. Okay, which one of you saw that mistake and didn't tell me about it? You should be ashamed of yourself.
I didn't see that mistake, but do we need to, if we're subtracting, do they both need to be cubic centimeters?
Oh, this is cubic centimeters. Good catch. So if I plug this into my calculator, I'm going to get that because this number is so small compared to that. It's like subtracting 1 from a bazillion. What's a bazillion minus 1? A bazillion. Bazillion is not even a word, right? At least I don't think it is, but let me show you what I mean. 8.181, whoops. I can't even hit ones correctly. 181 second EE negative 24. Whoa, where'd that log come from? I should just start all over. 8.181 second EE negative 24 minus 4.63 second EE negative 37. And look at what we get. 8 8.181 times 10 to the minus 24. These numbers are so ridiculously different that we don't need to bother subtracting the volume of the nucleus. Okay, so here the density is going to be, so I'm going to make a mistake here and see if you can find it. 9.11 times 10 to the minus 28 grams for an electron divided by 8.181 times 10 to the minus 24 centimeters cubed. And this is good to 3 zig figs, and so is this. So we're going to get 3 zig figs. So I get 1.11 times 10 to the minus 4 grams per centimeter cubed. And it's wrong. It's close, but it's wrong. What's wrong with it? Any ideas? Let me give you a hint. See, I think it's 30.
On my other screen right now.
So what's the issue here? Let's talk about this right here. This is the standard form for this isotope. How many protons does it have?
30.
How many neutrons does it have?
34.
How many electrons does it have?
30, right?
What did I use for the mass of my electrons on zinc? How many electrons did I use? The electron mass is blah. That's 1 electron.
Oh,
Yeah.
So how do I fix this?
10, 30.
Multiply by 30.
Oh, I see.
And we get 3.34 times 10 to the minus 3 grams per centimeter cubed. Now, when we compare these two numbers, can you see that the densities are vastly different? The densities are different by 10 to the 17.
Yeah.
And that's a huge difference. We call this 17 orders of magnitude, where every 10-fold difference is 1 order. So 2 orders of magnitude is 100 times different. 3 orders of magnitude is 1,000 times different. Are you with me there?
Yeah.
So these are orders of magnitude. So that is the last question here. We've got 2.3 times 10 to the 14 grams per centimeter cubed for the nucleus. We've got 3.34 times 10 to the minus 3 grams per centimeter cubed for the electron cloud or region. So we've got 17 orders of magnitude difference. So for all practical purposes, all the mass of an atom is in the nucleus. But the size of an atom is defined by where the electrons are. And that's pretty interesting. Okay, let's do this one here. A piece of nickel foil is allowed to react with fluorine to give nickel fluoride. The first question is, how many moles of nickel are there? Oh, this is all askew. And you can see there's probably going to be a B. This is the density. So we want to take this volume and calculate it. Now what I'm going to do though is I'm going to take that height and I'm going to change that to centimeters. I happen to know that for every 1 centimeter, there's exactly 10 millimeters. And that's something that you should know. If you're going to take a science class like this, something you should know. All right, so here we get 0.0550 centimeters. So now we can calculate the volume as 1.25 centimeters times 1.25 centimeters times 0.0550 centimeters. And we can calculate the answer here. We can even estimate the answer. 1.25 times 1.25 is about 1.50. 1.50 times 0.055, this is a tough one. But if I pretend it's 0.5, then it's half of this, so 0.75. But this is 10 times smaller than 0.5, so my answer should be around 0.075. So let's see what we get. And we get 8.594 times 10 to the minus 2 centimeters cubed, which is 0.08594 centimeters cubed. So this is the ish, and this is what we actually get. It's pretty close. I'm going to put an arrow going to the 9 because that's where I should round if I were done. But I'm supposed to figure how many moles. So what I'm going to do now is I'm going to take this and the density, calculate the grams, then get the moles. So I'm going to take the volume, turn it into grams, then turn that into moles. So I'm going to do that here. Now, why am I not writing nickel after each one of these? And the answer is, all of this only refers to nickel. I'm not mixing elements up. So it's okay to not put nickel there, but it's okay to put nickel also. So now I need the molar mass of nickel, which I can look up in the book. And I've got 58.69. And now that I'm thinking about it, I think I kind of want to put nickel in here. Okay, and we can estimate the answer again. 0.08 is really close to 0.1. 0.1 times 8.9 is like 0.8. 0.8 divided by 58 is like 1 divided by 58. So the answer should be like 1 divided by 58 would be not 1/2, but like 0.05. So 0.0 something is going to be my answer. And I get 0.01304 moles of nickel. And since this is my final answer, I'm going to go ahead and round to 3 significant figures because of this guy up here. So any questions about how to calculate the moles of nickel?
So at the very top where the D and then the subscript Ni.
Density of nickel.
Okay, density of nickel, and then, but I have the 58.69. Wouldn't that be?
58.69.
I mean, that's the, isn't
That's
that
not the density, that's the molar mass. 1 mole of nickel is 58.69 grams of nickel. So density has units of grams and centimeter cubed, not grams and mole.
okay?
So they're different.
And then how did you come up with it? Is that part of the question, the density of nickel, or were we supposed to just know that?
This is given.
Okay,
So all of this information was given, except for what I have below this line. This was my drawing to help me understand what I'm looking at.
oh, okay,
And then this is all the work to get to here. Kind of in a very linear fashion, if you will. To get the volume, I need length times width times height. I take the height, turn it into centimeters. So to get the volume, I multiply these things. And then I take the volume, multiply by the density, and multiply by the molar mass to get the moles.
okay.
And this is kind of my pathway, if you will, for what's going on down there. Okay, so we have 0.0130 moles of nickel. If we isolate 1.261 grams of nickel question mark fluoride, what is its formula? I don't believe this was given, but this is the reaction. Nickel is reacting with fluorine to give you NiXFY. And we know from the beginning part of the problem that the grams of nickel, well, actually, we don't have the grams of nickel. We need the grams of nickel. But we've already done the work to get that. We have 0.08594 centimeters cubed of nickel. And the density of nickel again is given, 8.902 grams of nickel per 1 centimeter cubed of nickel. If we multiply this and don't multiply by the molar mass, here's what we get. We get 0.7650 grams of nickel. Okay, so now we know that it's 0.76, so I'm going to rewrite this. 0.765 grams of nickel. We know that we get 1.261 grams of nickel XFY. How many grams of fluorine are there? And the answer is, if we subtract these two numbers, that should give us the grams of fluorine. Because in chemical reactions, you never lose mass. So if you end up with this from putting these two together, and this does not equal that, then the balance of this has to come from fluorine. So 1.261 minus 0.765 is 0.496 grams. So we have 0.496 grams of fluorine. And we need the moles of fluorine. Okay, so if I pretend that it's 0.4696 grams of F2, Then I multiply by 1 mole of F2 per 39.00 grams of F2. But then I need to multiply by 2 moles of F per 1 mole of F2 because I want to know how many fluorine atoms, not how many F2s. So if we do this work, we get 0.02544 moles of fluorine. Now, I'm going to circle this and show you another way to do it. Here's the other way to do it. Instead of assuming that we have grams of F2, just assume that we have grams of fluorine, pure fluorine atom. Let's see how many fluorine atoms we get this way. Oh, I made a mistake. This shouldn't be 39, it should be 38. So we have to go back and correct that. And we get 0.02611. And when we do this work down here, we get 0.02611. So even though we're getting into this part C, we're going to continue part B, and we need the formula. So we have 0.02611 moles of fluorine. And we know that we have, from the previous page, 0.0130 moles of nickel. So which of these two is the smaller amount, the nickel or the fluorine?
The nickel.
The nickel. So what we're going to do is we're going to do 0.02611 moles of fluorine over 0.0130 mole of nickel and see what we get. And we get 2.01 mole of fluorine to 1 mole of nickel. Do we think that is close enough to a whole number that we're going to say it's 2?
Yeah. I think so.
Absolutely. When you see 2.01, the 1 is a good guess, but it may not be exact. So could that 1 really be a 0? Absolutely. Could it be a 2? Absolutely. But it seems reasonable that it's probably a 0, and our formula is going to be nickel 1, fluorine 2. So that's the formula of the compound. What is the complete name? Well, here's what we need to do. First thing we're going to say is it's ionic. We know it's ionic because it has a metal and a nonmetal. We know it's ionic because it has a metal and a nonmetal. Secondly, if it's ionic, it has ions in it. The first element is going to be a cation. The second is going to be an anion. This is not a polyatomic anion. It's not like SO3 or SO4. So here we know that the fluorines are -1 because of the periodic table. We can just look at this periodic table and say, okay, column 8A, 0 charge. Column 7A, -1. And then so on, 0, -1, -2, -3, -4. So if we just memorize that, we know the fluorines have to be -1. What does the charge on nickel have to be if this formula is going to be neutral?
Positive.
Answer is +2. So +2, -1, and -1 equals 0. Now, how do we name these ions? This one is called nickel, but which are the ions that don't need a Roman numeral? And the answer is the ones in 1A, 2A, the metals in 3A, silver and zinc. So is nickel in 1A, 2A? No, nickel's right there. It's not 1A, it's not 2A, it's not 3A, it's not silver, it's not zinc. That means you need to use a Roman numeral. So what do we call this guy? Nickel 2 ion. These guys are called fluoride ions. And to put the name together, you call it nickel 2 fluoride. And this almost begs the question, well, if you write that name out, how do people know that there's 2 fluorides? And I'm going to show you that. So we give no indication of how many fluorides. How do we know there's 2? And the answer is this is nickel 2 plus.
Oh God, why am I so scared?
Fluorine minus 1. And we're supposed to do the old switch, right? Which means 1 nickel and 2 fluorides. And we don't write 1, so it becomes NiF2. So from the name, we can figure out there's 2 fluorides. Piece of cake. That's why we don't tell people there's 2. It's inferred. So I'm not sure, Jessica, if you're going to like this thing where you put the bigger one on top and the other one on the bottom. We could also have done it this way. And then rounded. Either way, you come up with the same formula, okay?
Got it.
I have a question.
Sure.
Can silver and zinc, can we write Roman numeral? Is it wrong or?
Silver doesn't use one, and neither does zinc.
So we cannot write it, right? Or
So-
can we?
If you see a compound that looks like this, what's the charge on the silver? +1.
Yep. 1.
Everyone knows it's +1. If you see this, what's the charge on the zinc?
1.
+2.
Wait, positive 2. Sorry.
And the way I like to remember these is this. If you look at the periodic table, you'll see these 3 elements form like a staircase.
Yeah.
And we know that aluminum's +3. Zinc is lower on the staircase, so it's a +2. And silver's even lower, so it's a +1. 1, 2, 3.
Okay.
That's how that helps me to remember silver and zinc.
Uh-huh.
Okay.
So even if it's a transmit metal, so it's still just 1, 2, 1 and 2
Well,
for zinc and
these are the only 2 transition metals where they have a fixed charge.
Okay, yeah. Yep, thank you.
Okay. So it's 106, but there's only one problem left to do. Let's go ahead and do it. This is a hydrate problem. If Epsom salt is heated to 250 degrees Celsius, all the water of hydration is lost. On heating a 1.687 gram sample of the hydrate, 0.824 grams of magnesium sulfate remains. How many molecules of water occur per formula unit? And this is all that we were given. And this was my hint to you to help you do this problem. So this is the formula of the hydrate that weighs 1.687 grams. When you heat it up, you end up with the ionic compound and no no formulas of hydration. And the formulas of hydration are over here because they have been separated. When you heat this up, the formulas of hydration do turn into a gas and they dissipate. So they leave the container, as long as you don't have the container sealed. So here, 0.824 grams remains, so that's got to be the mass of the magnesium sulfate. And as Anna was telling us before, the difference in these two masses will be equal to the mass of water. Now, we're assuming that whoever did this experiment heated this repeatedly until this stayed the same, so we made sure all the water was gone, okay? Now, to get the formula of this compound, what we want to do is take this information, the 0.824 grams of magnesium sulfate, and we want to take the mass of water, which I'm going to calculate now, 1.687 minus 0.824, and I better get around 0.8, right? So I get 0.863. And I want to get moles of magnesium sulfate, and I want to get moles of H2O. Now, for magnesium sulfate, magnesium is a 24.31, sulfur is a 32.07, and there are 4 oxygens, each at 16.00, and that's grams when I'm figuring out the molar mass. So when we add that all up together, it ends up being 64 plus 32.07 plus 24.31. And we get 120.38 grams. And this is going to round to right here. So this is kind of interesting. This has 4 zig figs, 4 zig figs. This ends up being 64.00, which is 4 zig figs. And we end up with an answer that has 5 zig figs. And that can happen with addition. For the moles of H2O, we've got 2 times 1.008 plus 16.00 grams for 18.016 grams. And this is good to hear because of this guy. So if we take our 0.824 grams of magnesium sulfate and multiply by 1 mole of magnesium sulfate per 120.38 grams of magnesium sulfate, we get a pretty small number. I think we could all agree. And we get 0.006845 mole of magnesium sulfate. And here we're going to get a pretty small number, but not as small as that one. Okay, so which one of these two numbers is smaller? And the answer is this one. So I'm going to do the 0.006845 mole of magnesium sulfate, 0.04790 mole of H2O. Oops, I did it the wrong way. You want to put the smaller number on the bottom. Okay, let's see what we get. 0.006845 into that. And I get 6.998 mole of H2O to 1 mole of magnesium sulfate. So that means we get 7.0. Well, this is, for all practical purposes, 7.00 when we round correctly. So our formula is going to be magnesium sulfate dot 7 H2O. Now, what's the name of this? And the answer is magnesium sulfate. 7 is hepta hydrate. Now, how come I don't use a Roman numeral for magnesium? And the answer is because you don't use Roman numerals if the ion is in 1A, 2A, 3A, silver, or zinc. And magnesium is in 2A, so I'm not going to use a Roman numeral for part of its name. So any questions on the formula of the hydrate here?
Can you write 7 as a subscript of H2O, or can you write?
Pardon me?
Can we write the 7 as a subscript of H2O with the with the parentheses? It's still the same, right? No.
No,
Okay.
you don't do that. Hydrates are always written this way.
Uh-huh.
And the reason for that is that when you write it this way, it makes it seem like this is a compound that when you turn it into this, it's chemically reacted. And it hasn't really chemically reacted. You just removed hydrations of H2O.
Okay.
So this is kind of a special thing where it's an ionic compound that can have H2O associated with it. And it's very easy to add the H2O and to take it away. So when it's fairly easy, it's kind of like a physical change, not a chemical change.
Mm-hmm.
So when you write it this way, it looks more like a chemical formula.
Okay.
Okay? So it's always written with a dot here and the hydration units of hydration in front of H2O. Always. In fact, there's another compound called called calcium sulfate. And it's a half. This is called calcium sulfate hemihydrate. And you can't have half of an H2O. So what this really means is this. There's 2 of these for every 1 H2O.
Okay.
And the reason this is called hemi is because when you look at the Earth, this is the northern hemisphere, right? And this is the southern. Unless you're unless you live in the southern hemisphere, if you live in the southern hemisphere, this is the southern and this is the northern. And whenever they look at maps, America is kind of like upside down. Did you know that when you go to South America, the maps and the globes are all upside down compared to what we like? Actually, I don't know if it's true or not. But if I lived in the southern hemisphere, I got a globe from the United States, I would take that sucker and turn it the other way around.
So is that the same what you were explaining before, like the CaSO4 part, the calcium sulfate? The reason why we wouldn't put parentheses around that and put 2, is it also have to do with the fact that it can be broken down easily?
Well, when you write formulas for these, you always write the ionic compound first. And only one. So you don't do this. You don't do that.
Mm-hmm.
So it's just a convention of how you write hydrates. You write the ionic compound without the hydrate and the proportion of hydrates per unit of ionic compound. It's just the way someone came up with writing these, and we follow that convention since.
So with the half in there, is that the correct way to write it?
This guy?
Yep.
This is the correct way to write it, but this is what it kind of means.
Okay.
Okay, so we don't write it this way. This is just what it means. And the reason it's called hemihydrate is because hemi means half.
Got it.
Okay.
Hemisphere. Okay, well, that's it. Thanks for listening, people.
Yeah.
Thank
Good
you.
luck on your exam today. I'll be posting some lectures later tonight and the next lab,
And
hopefully tonight, and then maybe tomorrow I can start doing a whole bunch of grading.
and then where in the book should we be at now?
You should be done. It depends on which book you're in. What text are you using? What edition?
The 10th.
You should be done with chapter 2, and you should be working your way to chapter 3 next.
Okay.
Chapter 3 is about, if I look at the title and tell it to you, chapter 3 is called chemical reactions. So you're going to be doing precipitation reactions, redox reactions, and we're going to be looking at acid-base reactions. So we're going to be doing 2 labs associated with that this week. The first lab is going to be the easier of the 2. We're going to be doing acid-base and redox reactions. And for that, you're going to need a penny and some vinegar. And you'll need the acid-base stuff from your kit to do the acid-base part. And then Thursday's lab is going to be precipitation reactions. And you have a little precipitation kit too.
Great.
Okay? And
Thank
you'll
you.
find those labs aren't too difficult to do, but writing out the information is a learning experience, to be honest. All right. Thanks for listening. Say your
Thank you.
goodbyes.
Bye.
Bye.
Bye, Jessica. Bye, Ann.
Bye.
Bye.
We'll see you Wednesday, I hope.
Yeah.
Yep.